Hi, everyone. My name is Will Cerny, and I'm going to be talking to you today about searching for the universe's faintest galaxies in our galactic neighborhood. And when I say galactic neighborhood, I mean the Milky Way. So I'm going to be talking about our efforts to find sort of the very lowest mass galaxies we know of in the universe in an environment where we are uniquely able to detect them. And before I go any further, I'd really like to thank the organizers for organizing this awesome conference and the opportunity to speak with you about this today. Before I go even any further, I really want to point out, this is a really nice optical map of the sky, and the brightest Milky Way satellites we can see with the naked eye. So these are the LMC and the SMC. We think there's something like 10 to the 9, 10 to the 10, 10 to the 8 in stellar mass. And so these have, many, many millions of stars. And sort of they're the polar opposites of the dwarf galaxies we're really interested in finding these days. And so to get sort of a global picture of what the sort of satellite system around the Milky Way looks like, we can turn to cosmological simulations. And so what I'm showing here is just sort of a particularly nice set of Milky Way mass hosts from a suite of dark matter only simulations called the Caterpillar Suite. And each image shows sort of a Milky Way mass host. The virial radius of the host galaxy is shown with that white circle. And what you can see from these images is that these galaxies are teeming with substructure. There's one large parent dark matter halo, the host halo, that the Milky Way lives in, but then there's sort of tens of thousands of these lower mass subhalos. And we think that reflects something about the fundamental assembly process of galaxies like the Milky Way. We think they assemble from the hierarchical merging of these tiny, smaller galaxies and subhalos, and many of those tiny galaxies and subhalos are sort of still out there in the Milky Way halo today, waiting for us to find them. Um, and so to sort of put that more concretely, if we look at that same simulation again, where the Milky Way disk, as you know it, would be sitting in the very center of that halo, and the virial radius is again drawn by that very large white circle, we can see that there's a bunch of large subhalos in this particular simulation. And you can imagine that the largest, most massive subhalo in the simulation hosts a galaxy, or dwarf galaxy like the LMC, which we know of it to be the largest, the most massive dwarf satellite galaxy of the Milky Way. But what you can sort of see in the background that aren't circled in white, again, are those tens of thousands of lower mass subhalos. And we think that some fraction of those subhalos host their own very low mass galaxies. And to make even more concrete statement, we think above about a halo mass of about 10 to the 8 solar masses, almost every one of those halos would host a little low mass dwarf galaxy. In those very low mass dwarf galaxies, sort of the lowest mass halos to host galaxies, we have these puny galaxies we call ultra faint dwarf galaxies. And so to sort of contrast that to the LMC, the galaxies we're looking for these days are something like 500 solar masses in stellar mass. So there's really a 10 to the 7 difference in stellar mass between the sort of brightest satellite of the Milky Way that we know of, the LMC, and sort of the cutting edge of what we're trying to find these days. And so to say a little bit more about those really faint galaxies that we're really interested in, these are the ultra faint dwarf galaxies. And so we sort of roughly categorize them with a cut on stellar mass or absolute magnitude, somewhat arbitrarily set around negative 7.7 in V band absolute magnitude, or about 10 to the 5 in stellar mass. And what's really unique about these galaxies is they're sort of some of the most extreme galaxies we know of in the universe. So the ultra faint dwarf galaxies are not only the least luminous and least massive galaxies in the universe, but they're also some of the oldest and least chemically enriched or most metal poor. And they're some of the most dark matter dominated galaxies in the universe. So, the ratio of their dark matter content to their stellar content is much, much higher than you would expect from a galaxy like the LMC or the Milky Way. In concrete terms, sometimes that can be as high as, say, 1,000 times more dark matter than stellar mass. And so these really extreme galaxies are of great interest to find, but unfortunately, their very faint and diffuse nature makes them rare gems. Um, the funniest coincidence there, though, is that they're actually expected to be some of the most common galaxies in the universe, just sort of by virtue of the halo mass function increasing as you go to lower masses. And so you have this paradox where they're extremely hard to find, but also some of the most common galaxies you expect to find. To make that faint and diffuse nature really explicit, I'll sort of invoke a cliche with some of these ultra faint dwarf galaxy talks, which is to show you an image of one of these, or what they look like in sort of a large scale size survey. And so what I'm showing you is that same dwarf galaxy I showed you a couple slides ago, which is called Segway 1. It was actually discovered in the Sloan Digital Sky Survey about 15 years ago. And sort of what you can see in this image is nothing. You see sort of this diffuse field of stars. It's not just the projector. You really can't see anything clearly. But the galaxy is there. And so the first important thing to note is that we're looking for systems that are resolved into stars. So you're not expecting to see sort of a central, diffuse blob like you might in an extragalactic context. you're looking for sort of a clustering of stars in the background of these images. And so this is just something to keep in mind, and I'll get back to about how we find these in just a minute. For a little more about why we care about finding them, um, exactly how many of these galaxies there are is a pretty strong probe of the nature of dark matter. So we think that if we can count up the number of these faint galaxies, we can say something interesting about the parent subhalo population around the Milky Way. And that dark matter subhalo population of the Milky Way is sort of very dependent on what dark matter particle model might be out there in the universe. And so if we had a very cold dark matter particle like the WIMP that we know and love, you might expect a picture like you see from the simulation on the left, where again you see this picture of a Milky Way mass galaxy teeming with these low mass halos all around it. But if you had a warmer dark matter particle, something like a sterile neutrino, for example, those particles can free stream easier. And so they essentially smooth out structure on small scales. And so you get far, far fewer of these low mass halos that host these ultra faint dwarf galaxies. And so in other words, what we can try to do is if we find a certain number of dwarf galaxies, we can attempt to rule out these models which suppress small scale power. We can actually do the same with baryonic processes as well in galaxy formation. So I'm showing sort of two cartoon examples of how that might work. So in the left, I'm showing sort of the number of dwarf galaxies you expect above, above a certain mass m as a function of mass or absolute magnitude, your favorite variable, where the faintest galaxies on this plot would be on the far left. And in a model of galaxy formation where you have cooling through a purely atomic hydrogen, you actually predict a far fewer number of these faint galaxies than if you had, say, molecular hydrogen available as a cooling mechanism. And sort of that reflects one of the ideas that's central to the formation of these galaxies, which is that the main limiting factor is whether you can cool and condense gas into halo and form stars before cosmic reionization comes along and sort of boils away your gas. And so a sort of a different view of the similar sort of phenomenon is on the right-hand panel where I'm showing the fraction of galaxies hosting fraction of halos hosting a galaxy. So what we call the occupation fraction as a function of halo mass m. And so at the very highest masses on the right-hand side of this plot, you expect essentially all the halos to host galaxies. But as you go to lower masses, it depends a lot on when reionization occurred. So if you have a very early reionization, so at high redshift, you actually can form far fewer of these galaxies simply because you haven't had time to condense and cool your gas to form stars. And so these are just sort of toy examples of how these faint galaxies can be used to place really strong constraints on dark matter and galaxy formation physics. All we need to do is find them. All we need to do in air quotes. In other words, we need to find these galaxies, and I'm going to tell you now about how we actually go about in doing that. To mix metaphors a bit, this is a rare gem in the haystack problem. So we're looking for rare objects amidst the sea of Milky Way foreground stars. And so again, I'm showing you this optical image of the Milky Way with the galactic plane at the top and the LMC and the SMC in this the bottom. And in the Milky Way, we think there's something like 100 billion stars. And the sky is about 41,000 degrees, something like that. The objects we're looking for are resolved clumps of stars. Something like 100 detectable stars is something reasonable to expect from current surveys. And so it looks like the exponent got carried down to the next line, but there's something like a 10 to the 8 difference in the number of stars you have in the Milky Way and the number of stars in these systems. And so you're looking for a very small contribution to the Milky Way halo. You can pose the same sort of statement in terms of angular area. So again, the full sky is something like 40,000 square degrees. But the UFDs, the ultra-faint dwarf galaxies we're looking for are something like a few arc minutes squared or smaller. And so that's about a factor of 10 to the 9 in spatial area. We have to sort of comb through and find these faint galaxies in. One thing I'll add already here is that this is completely ignoring that there's also a background contribution from contaminating galaxies, right? We think compact galaxies look a lot like stars, and that sort of star-galaxy confusion tends to be one of the main limiting factors as we try to find these galaxies. So it's not just Milky Way disk stars that are sort of in the foreground of these galaxies we're trying to find. It's also the background galaxies, which sort of look a lot like the rare stars in these galaxies we're trying to so now I want to show you sort of a summary of how we've done over the last 70 years in this field. So what I'm showing here is the cumulative number of these ultra-faint dwarf satellite galaxies we know of as a function of time, starting in the year 1900. And so before some 1900, we only knew of the LMC or SMC, which is why this plot starts at n equals 2. And one thing to note on this plot is the y-axis is changing dramatically. And so, by the 2000, we know of something like 10 of these galaxies. But then after 2000, we see this monumental spike in the number of galaxies we know of. And then here at the end, I'm showing you what we expect from Rubin. So I know that kind of went by quickly. I'll wait for it to start one more time. Oh, so again, we're starting with just the LMC and SMC. Those have been known for millennia. And it wasn't until the late 1930s that we knew of any other dwarf satellite galaxies in the Milky Way. So we went from 2 to 4 rather quickly. It went sort of incrementally up all the way until 2000, roughly. And then something dramatically changed. And that's really exciting. And I'll tell you about how that's possible in a minute. So again, we've now shot up to something like 60 known systems. And if you believe what the semi-analytic models tell you, we might expect something like 400 to 500 of these galaxies in the 10-year Rubin LSSD dataset. So there's a lot left to find. As to how we find them, we started by finding them through good old visual inspection. So what I'm showing you here is sort of a fun plot from Harlow Shapley's 1938 discovery of the sculptor dwarf. And he's basically drawn out the distribution of stars in this area of sky, and there's sort of a clustering of stars that's conspicuous. And it was sort of found by coincidence. You know, you take a lot of plates in a sky survey, photographic plates that is, sorry. You visually inspect them and hope you find something interesting. And here he flagged it as a new stellar system of a new type. Nowadays, though, we can do a lot better. So rather than using photographic plates, we now use digital sky surveys. And in particular, the Sloan Digital Sky Survey is responsible for that big first spike in detections of these faint galaxies. So starting in about 2005, we learned of the first of these ultra-faint dwarf galaxies. And then starting in about 2015, when the dark energy camera came on, we sort of doubled the number again of how many we know. And there's a number of other instruments which have contributed to this as well, including the Hypersuprime camera, Pan-STARRS, Gaia, etc. But I'm particularly going to focus today on the dark energy camera, which is responsible for a large fraction of these satellite detections. In detail, we find these galaxies through looking for spatially localized overdensities of old metal poor resolved halo stars. So essentially, we're playing a game of clustering. We're trying to find a signal against a smooth background. And the way we do that is by surveying large swaths of the sky. We tease out the stars from the galaxies. We then filter for those old metal poor halo stars. We construct stellar density maps, which look like the one I'm showing you on screen. We smooth those density maps with the spatial kernel. We then look for statistical overdensities, so sort of Poisson peaks against the smooth background. And then we try to visually triage the detections into what we think are real galaxies. And so what I'm showing you in this cool plot on the left is a sort of a view of the stellar density as seen by Gaia for halo stars that are blue horizontal branch stars. And so we think blue horizontal branch stars are sort of a type of old low mass star that happens to show up a lot in these dwarf galaxies. And so if you filter for those old halo-like orbit blue horizontal branch stars, you get this beautiful smooth background. It's kind of hard to see probably at a distance. But then you see this wonderful like black little overdensities popping out of the map, a bit like speckles. And that's exactly what we're looking for. These just tiny clumps of excess stars compared to what you expect from the smooth background. And we think that these are the locations of dwarf galaxies or star clusters in the Milky Way halo. So to tell you a little bit how we do that filtering for old and metal poor stars, we can exploit the fact that the ultra-faint dwarf galaxies are ancient metal poor stellar populations. And that's really a ubiquitous statement. Every ultra-faint dwarf galaxy we've found sort of obeys the same sort of stellar isochrone. And so what I'm showing here is a good old HR diagram of, luminosity versus color. We see sort of an extended main sequence at the bottom, a red giant branch, and then those blue horizontal branch stars. And we think that most, all of the ultra-faint dwarf galaxies can be reasonably explained by an old metal poor stellar isochrone. And because we expect sort of the luminosities and colors of stars to follow along that track in the HR diagram, we can apply what we call a matched filter technique. So we can basically filter for stars that fall along that HR diagram track, which is shown by that black moving line in the left-hand panel. And so what I'm doing is I'm filtering the color magnitude diagram or HR diagram in the left panel to select for stars that are only consistent with that template isochrone shown in black. And then we basically do the filtering and plot up the stellar density map, which is shown in the right-hand panel. If you don't see anything, then what you do is then you shift this isochrone down in distance. So the reason why it's going down is we're scanning across a large range of distances in the Milky Way halo. And what you can see is that when that template sort of lines up with what you can sort of see around D of 20 maybe on that plot, is the blue horizontal branch, you see the signal pop out in the middle of the plot. And this is the real detection of an ultra-faint dwarf galaxy called Eridanus 4 with the dark energy camera. In practice, we can do a little bit more sophisticated things like this. And so as an example of things we can do, well, we expect more main sequence stars than red giant stars in these systems. So we can weight stars that we think are consistent with being main sequence stars more highly than red giant branch stars, which are more lost in the disk contamination. And we can play other games like that to try to optimize these matched filters to simultaneously maximize the signal, so the number of filtered stars in these galaxies we're picking up on, and minimize the contamination from the sort of disk population. And so, yeah, we're basically looking for these smooth stellar density backgrounds with these sharp peaks in the middle. The way we do that across the whole sky is highly in parallel. So we basically split the sky into Helpix pixels, if you're familiar. We use about 3 degrees squared pixels. And we basically run that algorithm across a range of distances and every single pixel independently. And then we basically look for those tiny bumps in the stellar density maps that pop up. And so I'm here showing 6 that we discovered just last year from the Delve survey, which is a big effort to map the southern sky with the dark energy camera. And, you know, they all look kind of similar. You know, we're looking for these tiny black blobs on these homogeneous maps. And we're good at finding them this way. You know, one thing I haven't said so far is using machine learning. This is actually a task that we haven't historically relied on machine learning for, and yet we've somehow been very successful. And so at the very end of this talk, I'll talk about ways we might be able to augment this procedure using machine learning to do a little bit better. One area where that is potentially relevant is false positive elimination. So you just had a good look at those, you know, tiny detections, which we think are all real systems. But these are all false positives that were detected at high significance with the Cypher algorithm. And fundamentally, these maps maybe look a little messier, but they're mostly the same, where there's some kind of background, and then there's that peak in the middle that we've identified with this algorithm. And so some examples of false positives that show up in our searches are galaxy clusters. So as I alluded to before, star-galaxy separation is a major issue. We sometimes run into issues with the galactic foreground. So this happens to be the middle panel, some shredded galactic cirrus components that the catalogs from dark energy camera think are stars. And then occasionally we have spurious sources induced by bright stars. And so we get a lot of fake detections that look a lot like this, and it's sort of a game to try to tease out the real detections from all the ones that look like this. When we do detect something, it often looks like this image on the left, where you have a few barely resolved stars, maybe some faint blur of partially resolved sources in the background, and we'd really like to say whether they're real or not. And so when we want to do that, we usually turn to a large aperture telescope. So here I'm showing follow-up imaging of this particular low luminosity system with the Gemini telescope. And while it's pretty obvious that there still aren't that many stars in the right-hand panel, you clearly see that these objects that are sort of faint and fuzzy are resolving into stars, and that tells us a lot about whether this is a real old stellar population like we expect. In color magnitude space, you might have the same plot look like this. So in the left, I'm showing again the sort of discovery data you might get from the dark energy camera, where there's only maybe a small number of bright red giant branch stars. It's sort of weakly follows this isochrone sequence shown in red. But then if you were to go get Magellan megacam imaging, like I'm showing here, you can often resolve the old main sequence turnoff feature, which is sort of a staple of your old stellar populations, and then resolve a large number of faint main sequence stars, which sort of build up the statistics you need to say something about the structural properties of these galaxies. So, measuring their sizes, measuring their distances better, et cetera, et cetera. So to tell you a little about how we've done sort of in aggregate, what I'm plotting here is absolute magnitude, which is a rough proxy for stellar mass, versus half-light radius, so size. And so in the top left of this plot, we have the sort of bright globular clusters. These are 10 to the 4, 10 to the 5 solar mass objects. We think they have no dark matter, just bright clusters of stars. And in the sort of right-hand quadrant of this plot, we have the ultra-faint dwarf galaxies, which sort of follow these diagonal lines of constant surface brightness. And what you can see again is there's this sort of enormous dynamic range where we have systems that are 10 to the 8s in stellar mass, down to systems that are all the way as faint as 100 solar masses in stellar mass, or even fainter. And there are really two sort of thresholds we think are interesting to try to cross in the Rubin era. One of them is the surface brightness frontier. So those diagonal lines I'm showing in this plot are lines of constant surface brightness. And one thing we don't really know is whether there are systems that are even more faint and diffuse sort of in the bottom right of this plot. And so that's something we'd be interested in finding. Another sort of class of systems we're interested in finding are these very compact, faint Milky Way satellites at an absolute magnitude sort of near zero or even fainter. So these are entire star clusters or dwarf galaxies, fainter than, say, a single horizontal branch star. The entire system fainter than a single horizontal branch star. And actually, the very faintest system we know of is an absolute magnitude of +2 or 16 solar masses. And so one of the really interesting things with Rubin will be trying to see whether there are even more of these extremely low luminosity systems in the bottom left-hand quadrant of this plot. To make the Rubin discovery potential a little more concrete, what I'm plotting here in the middle panel is the number of dwarf galaxies we expect as a function of absolute magnitude. And in the black line, we're showing sort of the observed counts. So again, the 60 odd galaxies we know of around the Milky Way today. And in the blue and then the colorful points are predictions from Rubin. And it may be hard to read from the distance, but sort of the consensus from multiple different groups who have done this modeling is that we can probably expect something like 200 to 400 total Milky Way satellites, meaning we have something like 200 to 300 left to find. And the majority of these systems are sort of on the far left of the plot here, meaning that these are going to be the systems that are 500 solar masses or fainter. So extraordinarily faint systems in great number in the Milky Way halo. And the big challenge of Rubin will be trying to find them. We think that Rubin should be able to do this. So this right-hand plot is showing, what we expect from the population of these satellites as a function of surface brightness. And we think Rubin should be able to probe the surface brightness limits needed to find most of the systems in the halo. One major complication, though, is star-galaxy separation. So at the very faint magnitudes probed by Rubin, we have a bad problem with confusing compact background galaxies with stars. And because these systems have so few stars in them intrinsically, you really value purity and you really value completeness. But at the faint magnitudes that Rubin's going to reach, like 25th magnitude, these background galaxies will outnumber stars by 10 to 1 or even much more than that. And that's what this plot is showing. The details don't matter so much. And I thought it was rather amusing. This is a problem that's plagued us even since the discovery of Sculptor in 1938. In Shapley's paper discovering Sculptor, he actually remarks on whether he initially thought this entire dwarf galaxy was just a cluster of galaxies, like the one in a galaxy cluster he was studying. And so this is a problem that's plagued us for a long time. It's plaguing us with current surveys, and it's going to plague us with Rubin. And so I think it's a promising area where we'll be able to continue to improve with machine learning. I'm running a little low in time, so I'm going to sort of speed through this. But another area where we think that Rubin will be able to play a role is how we go from sort of the initial candidate pools provided by these systems, which can be as large as, say, 10,000 detections, to the 200 or 300 real satellites that we expect from Rubin. And there's been a lot of creative ways that people have tried to do this, including by people in this room. And then lastly, the one area I think that we've already sort of mastered the art of machine learning for is trying to quantify and interpret our sensitivity to these systems. And so one way we've done that is, we've injected simulated dwarfs into our dwarf search data sets, run our codes, and then seen what we recover. And rather than use machine learning to actually detect these systems, what we do is we use sort of a random forest model to predict our sensitivity to these systems, both real and simulated, as a function of properties. So, use a random forest model to make a sort of a quantifiable statement about what is the likelihood we could discover a given dwarf galaxy with this distance, this stellar mass, this surface brightness. And then what that sort of random forest model would allow you to do is hand it to your theorist friends, and they can compare what their simulation suggests to the observed data by way of your sort of observational selection function. And so this is something that's been done, and that has really allowed us to make these detailed comparisons between observations and simulations that are needed to say something about dark matter and galaxy formation physics. So I'm going to stop there and leave my summary slide. But I will say the future is both very bright and ultra faint with Rubin. And I'm really excited to see what we can find in the next few years.